Hey guys, imagine you are trying to decide who the best football player is. Definitely by analyzing their data with the features like total goals scored, total number of passes that player made, and total minutes he played. Goals scored might be in the tens or the 20s, while the number of passes and the minutes he played are usually in hundreds or the thousands. So without standardization, PCA will be heavily biased towards minutes played because it is in hundreds or the thousands and making it seem like the most important factor. But we all know what is the most important factor here. Definitely, total number of goals scored has the more importance than the total minutes he played, and we all know that. But here, if I don't use standardization, PCA will bias towards the larger numbers, and it's like using a broken scale. This is what happens when you skip standardization in principal component analysis. So in this particular video, we are going to talk about effect of standardization in PCA, why standardization matters in principal component analysis, how the standardization affects PCA, and definitely what I don't see, I don't believe so. We are going to talk about the demo. We'll see the demo to understand the effect of standardization using Jupyter Notebook and sklearn library. So stay tuned, make sure to watch this video till the end, and let's get started. Hey guys, welcome to AI with AI. This side Asif Imnad. Principal component analysis, or a PCA, is a dimensionality reduction technique that simplifies complex data sets into the smaller set while still maintaining its significant patterns and the trends. And we know that it does this by transforming the original variables into a new set of variables called principal components. The idea of PCA is very simple. It reduces the number of variables of a dataset while preserving as much information as possible. We already discussed PCA in detail in the previous video. If you haven't watched that video, I urge you to watch that video first and come back to this video. This is in continuation with the previous video. I'll keep the link in the description and also on the I button above. First thing first, let's understand what is standardization. We also discussed standardization in detail in the previous videos. You can also find the link in the description. But in short, to understand, standardization transforms your data, right? So it has a mean of 0 and standard deviation of 1. In simple words, it centers the variables at 0 and sets the variance to 1. And how it does that? By calculating z-score, right? We discussed this in the previous video already. Meaning, it puts your features neatly packed within the bell curve. You see this? The data before standardization, mean is at 79. But if you see after standardization, mean shifted to 0 and variance became 1. Whereas before standardization, variance is something different. Variance is 2589 and standard deviation is 51. But after standardization, mean shifted to 0 and variance become 1 and the deviation become 1. So this is what standardization does. And yes, this helps with distance-based models like Support Vector Machine and K-nearest neighbors. This is the data which you see on the screen, 3 different examples, right? And PC1 and PC2 calculated on each one of these, right? If you see more linear data, less variation, right? This is PC2, which calculates the variation, and PC1 calculates the distances. The first component captures the most variations and the second component captures the maximum variance, which is orthogonal to the first principal component, and so on. So PCA is all about finding directions of maximum variance. If your features have widely different scales, PCA will get tricked into thinking that features with the large values have more variance than they actually do, which is not always true. As I gave you the example in the start of the discussion, right? Let's understand that with the football example again. So the data given for this particular football player is total number of goals he scored and total minutes he played. Definitely total minutes played will be in the hundreds and total goals scored will be in tens, 20s, right? So now you imagine if I apply PCA dimensionality reduction to this, which component or which feature will be selected first? So PC1 will be drawn against the most variation, which is total number of minutes, right? This is the PC1 line because it has the maximum variation. It draws the best fitting line over the data, and total number of minutes played is bigger compared to total number of goals scored. But do you think that minutes played is more important than the total number of goals scored? I don't think so. And when it draws the PC2 line, it looks something like this, which is orthogonal to the PC1, right? And this is how the new table PC1 and PC2 would look like. So this was the original data before, and after applying PCA, this is what we see. Basically, it captures the variations and the variance, right? So if you see, values for PC1 are more, which is total number of minutes he played, and values for PC2 are smaller, which is total number of goals scored. And PCA is the dimensionality reduction technique. If I want to drop any of this column, which column I would drop? Definitely I would drop PC2 column, right, which is total number of goals scored, which is not a good idea. This is where I see PCA will be heavily biased towards minutes played, towards the bigger numbers. That's why standardization. I hope you understood this with a very simple example here. Now let's see this practically. I'll jump onto the Jupyter Notebook.
Okay, before we proceed and discuss in detail, if you are new here, don't forget to hit that subscribe button and the bell icon so that you won't miss our latest videos on AI. We see you are watching our videos, but 90% are not yet subscribed. We put a lot of efforts creating these videos for you free. Keep us motivated by liking and subscribing, so YouTube algorithm will also help us reach more audience. So, did you subscribe and like? Thank you.
Alright, so here I am on the Jupyter Notebook. So we have seen feature engineering, regression, classification, clustering, anomaly detection. All these demos are already uploaded on our GitHub repositories so that you can also try on yourself. The link for this GitHub repository is also given in the pin comment. You can find that. Okay. So currently we are in PCA. So I'll go to 5 PCA. We have seen this demo already, learning PCA and applying PCA. Today we are going to talk about effect of standardization on PCA. So this is the actual practical implementation of PCA. We don't really apply PCA directly on the data, but before applying PCA, we make sure that data is standardized, because standardization is important in distance-based algorithm, right? Like SVM, KNN, and it is not really important for the tree-based algorithm. Okay, let's see the demo here. I have the notebook open. Okay, so we are gonna see this effect of standardization on PCA for classification of wine data. We're gonna use wine dataset here to classify the type of the wine and the quality of the wine to see what is the effect of standardization on the PCA. So first thing first, import the libraries. I'm gonna use pandas as a data frame because I need a data frame to work on the data. Import the data here, read CSV because I have the data here under datasets, wine.data. So this is our CSV where I have the data, df.head to see first 5 rows. You see, if you observe this closely, some numbers are given here. We don't really worry about that. So only one thing that we need to understand is column 0, feature 0 is about the type. This is our target column. Basically, column 0 defines the type of the wine based on the data given here. So if I see it here, df.0 values count, it shows the count for the type 1, which is 59. For type 2 wine, it is 71, type 3, 48. So it classifies the type of the wine or the quality of the wine based on certain parameters here. Okay, so what do we need to do here? So first thing, we will see the accuracy of the model without using standardization and without using PCA. Okay, we'll simply use one of the machine learning algorithm, classification algorithm. Here, for example, we are using Gaussian naive Bayes. You can use SVM or KNN, whichever algorithm you are comfortable with. And later on, we will see how the accuracy changes, how accuracy gets affected when I start applying PCA. And on top of PCA, when I apply standardization, how accuracy improves. So let's see that here. So first thing first, I will have to divide the data into training and testing. So I'm going to divide my data into training and testing. 70% is my training data set and 30% is my testing data set. And this is the count you see here. Data set is small, but doesn't really matter. As I've said, I'm going to use naive Bayes classifier on original dataset, and this is without applying PC. Initialize Gaussian naive Bayes, model.fit, xtrain and ytrain. Training data I have provided, and now let's evaluate the performance without applying anything here. This is just the algorithm initialized, model.fit and model.predict. Okay, this is what we're gonna do without standardization, without PCA. Okay, just to see before and after. So model.predict will give me the prediction accuracy for the training data set without PCA and also without standardization. We haven't applied anything yet. All right, and also on the test data, we want to see the accuracy here. So let's execute this. So I see the prediction accuracy for the training data set without PCA is 98%. And prediction accuracy for the test dataset without PCA is 94%. Okay, without PCA and also non-standardized data. One thing to notice, accuracy here for trained data is 98%, but for the test data, it is comparatively very low. It is 98 for train and 94 for test data. Now let's go one step further. and apply standardization on the data, and let's see the effect of standardization on the accuracy. So we already know that how to use standardization. We have created a bunch of different playlists, different videos on feature engineering. That complete playlist is available. I will also keep the link here in the I button. If you are not aware about how to use standardization, what algorithm, when to do that, everything you'll able to find in that playlist. Go check that out. But for here, to standardize the data, I'm using pre-processing. I'm importing pre-processing.standard scalar fit on train data, and we know that the function that we use is a transform. So after a transform, this is where standardization will happen, meaning the mean will be shifted to 0 and deviation variance will be 1 for train data and the test data. Now let's apply Gaussian naive Bayes on top of this new data. Okay, X-train standardization, X-test standardization. This is still without applying PCA. Okay, we haven't seen PCA yet. Let's see what is the accuracy I will get on standardized data. I have initialized Gaussian naive Bayes, this time model.fit, but this is on new dataset, which is after standardization and not the raw one. X-train, Y-train is our raw data without applying standardization, without applying PCA, of course. Okay, now let's evaluate the performance. And model.predict, definitely on standardized data, X-train standardized, and model.predict on X-test standardized. Let's see the accuracy this time. Do you see any difference? 98.39. So this is the prediction accuracy for the standardized training dataset without using PCA yet, 98.39, and on the test dataset 94.44. What was before? 98.39, 94.44, 94.44. There is absolutely no difference. This is exactly the same. But where is PCA? Our main goal is to see PCA, right? So let's use principal component analysis. Currently, we have considered all these features, but PCA is all about reducing dimensions, right? We want only 1, 2, or 3 dimensions, which are more important. So we need to reduce the dimensions, and we do that by using PCA, right? So now let's use principal component analysis on both the dataset. So now we are going to perform PCA on standardized and non-standardized dataset so that you will understand the difference. What will happen if I apply PCA on standardized data, and what will happen if I apply PCA on non-standardized dataset? All right, let's see that. Very first thing, import PCA, sklearn decomposition, initialize PCA. It is very simple. The number of components is important here. How many components you want to consider? How many dimensions? 2 dimensions, right? I want to reduce from these many features to only 2 dimensions. We discussed during theory that how it converts original data to 2 dimensions. And after that, model.fit on the training dataset. PCA is not a machine learning algorithm. Keep that in mind. PCA is a pre-processing technique. Okay, so that's why we do not have predict method here. We have transform method. Same like feature engineering. So in standardization, also in feature scaling, if you see, we have transform methods. Whereas for machine learning algorithms, we have predict methods. Here we have transform method. So let's transform training data and let's transform test data. And if you see, we are doing it on X-train. That means this is without standardized data. Okay, this is non-standardized data. And same thing we are going to do on the standardized data. We again initialized PCA, X-train standardized, X-test standardized. Okay, let's execute this. So we have 2 PCA trained now. One is simple PCA on non-standardized and one is PCA on standardized data. Now let's quickly visualize this, how our new features will look like. And for that, I'm going to use matplotlib. Currently, don't really worry about it. I'm just plotting the data in this format, okay, blue, red and green, which will represent different classes, different types of wine. And one plot will show how the data will look like without standardization, and the other plot will show PCA after applying standardization. So this is what we wanted to see. Let's plot this and see how it looks like. Beautiful. Transform non-standardized training dataset after PCA. You see this? Very much mix and match. This is, we applied PCA, but no standardization applied. And here, if you see, segregations are much clearer. I can easily segregate the data here. You see that green, red and blue. If I compare these 2 plots here, so this data is after standardization. So what we did here, we took the raw data, we applied standardization on the data, and we applied PCA on top of this, right? So you see this, this is the effect of standardization on principal component analysis. This is the effect of non-standardization and only applying PCA. So now you only tell me, where will we have better accuracy? For sure here, right? We have more clear distinctive classes here. Let's see what is the accuracy that we get here. And the difference is, this time I'm using the raw data to train, which is non-standardized, and here I'm using standardized data, right? So let's see what's the accuracy I'm gonna get. So evaluating the classification accuracy with and without standardization by using PCA. Okay, so this time our X-train and Y-train is non-standardized data, but PCA applied on top of this data. Okay, so if you see here on top, okay, X-train, X-test, this is PCA, but standardization not applied, and X-train standardized, X-test standardized is PCA and standardization applied. Let's see the effect of standardization on PCA here. Okay, so prediction accuracy on training for PCA without standardization, it is 76%, and prediction accuracy on testing for PCA with standardization is 79%. Okay, so without standardization, this is what the accuracy I'm gonna get here. Basically, I applied only PCA here, not standardized, right? 76 and 79. The accuracy is drastically reduced, right? Because PCA is dimensionality reduction technique. There is a loss of data. Now let's see the accuracy on standardized data and also after applying PCA. X-train standard and Y-train, X-train standard and X-test standard here. Model.predict, X-train standard, model.predict, X-test standard. So this data is our standardized data, right? X-train standardized, X-test standardized. This is what we did before on standardized data, right? Now let's see what is the accuracy that we get. So we did everything here. We took the raw data, we applied standardization, and on standardized data we applied PCA. This pre-processed data we gave to Gaussian naive Bayes, we did model.fit, right? So this data is after applying standardization and the PCA, and this is the accuracy that we get. 95.97 is the accuracy that we get on the training dataset, and 98% is the accuracy that we are getting on the testing dataset. Let's compare this before and after. 95 and 98, right? And let's see. So without standardization, this is really low, right? It reduces the accuracy drastically. Okay, not a good idea, because PCA is a dimensionality reduction technique. You loses the data here, right? Okay, so this is the original accuracy without applying PCA and also without applying standardization. 98, 94, and after applying PCA and standardization, 98, 94. For training dataset, I don't really care. I want to improve testing accuracy. So previously the accuracy was 95, but now it is increased to 98. And you can see a huge difference between the non-standardized data accuracy here and the accuracy here. Beautiful, isn't it amazing? The visualization itself shows everything clear, right? So this is PCA applied on non-standardized data and PCA applied on standardized data. Definitely accuracy will increase here. But sometimes, you may not understand how many components I should consider. So this accuracy we are getting only for PC2. Number of components we considered is 2. But how many components I should consider? 2, 3, 4, maybe, right? Total number of features that we have here in the original dataset is 13. But how many components we should consider? So if you fine tune that, if you identify the correct number of components, then accuracy will be more better. And to understand how many total number of components we should get, we need to identify that correct number, right? Not to overfit and not to underfit, right? And we can visualize that by using interact method here. So I'm going to provide the PCA variance from 0.01 to 0.99. Basically, I'm passing different number of PCA variance. You see that? I'm passing it dynamically. I'm going to check what is the accuracy I'm going to get if I change the number of components here. This is what we did, okay? And we're going to also see the prediction here. So let's execute this. Okay, after execution, what do I get? So if I change the variance, currently variance is 2, 95, 98. So this was the original thing, right? So this is what we have also got here. PCA was 2 before, right? So now if I change the PCA value, if I change the variance, you see the accuracy for training and testing is changing, right? So it should not be highest, right? 0 to 1. Why? Because data is standardized now. Variation needs to be in between 0 and 1. So when I keep the maximum variance, that means you are considering all the columns. But then what is the use of using PCA, right? We need to find the trade-off, overfitting and underfitting. Okay, so I need to identify the correct number of components where I get the better accuracy for testing and training as well. Okay, so if I change it to 3 components, 3, then testing accuracy becomes 100. So this means it's getting overfitted. So that's why principal component 2 is the better value for this particular example here. All right, I hope you found this demo interesting, and we have discussed effect of standardization on dimensionality reduction technique, which is PCA. Why standardization matters in PCA, how the standardization affects PCA, and also the demo.
And that's how we come to an end of this video. If you have any questions regarding the same, let us know in the comment below. If you found this video helpful, please subscribe to my channel and hit the like button, and don't forget to share this video with your friends and the colleagues. Thanks for watching. See you again next time. Till then, take care and bye bye.